This is topic 10.14, finding Taylor or Maclaurin series. So this is a really important topic because there is going to be some memorization. So let's go ahead and jump right in. If f of x has derivatives of all orders x equal to c, then a Taylor series may be formed that is equal. That is very powerful. That is equal to the function for many common functions. And let's go ahead and revisit this. So we have our Taylor series is f of x is equal to, and I'll go ahead and write the sigma notation first, n equals 0 to infinity of the nth derivative evaluated at c divided by n factorial multiplied by x minus c to the nth power. Now, we talked about how our first term of our Taylor series is always going to be f at the center, the function evaluated at the center, and that always seems to get us started. And that's the 0th derivative, you could say. So now we have the first derivative evaluated at c multiplied by x minus c to the first power plus the second derivative evaluated at c multiplied by x minus c to the second power, and that is divided by 2 factorial and so forth. Okay? So we kind of do remember a bit of that. See if I can move this over just a bit. And that way I can get those dots in. Okay. So what about if the center is 0? You guessed it, we have a Maclaurin series. I will tell you, we will be working more with Maclaurin series at this point than Taylor series. So the center will be 0 quite often. Now, here's where the memorization comes in. You need to know the following series. You will need to know the Maclaurin series for e to the x, cosine of x, sine of x, and 1 over 1 plus x. So all of those will need to be memorized. Okay? The Taylor series, this is really, really important. The Taylor series of these functions are exact when we go to infinity. So we are actually coming up with an exact infinite series that equals that function. So it's a pretty cool thing. So let's go ahead and see if we can talk about both of these series and kind of generate the Maclaurin series for e to the x and the sine of x, and kind of talk about some ways we could have some help memorizing these. Okay, so for e to the x, keep in mind that how we are going to write these is we are going to start with the function is equal to, remember we said f evaluated at the center, plus the first derivative evaluated at the center. Of course, the center is 0. Plus the second derivative evaluated at 0 times x squared divided by 2 factorial plus ... Okay? So what do we have? We have e to the x is equal to, and e evaluated at 0, e to the 0 is equal to 1, plus the first derivative evaluated at 0, of course, is going to be 1 times x divided by 1 factorial plus the second derivative evaluated at 0. If you can see, let's make a note here. F of x equals e to the x, and the nth derivative of x is equal to e to the x for all x. And so we know, therefore, the nth derivative evaluated at 0 is equal to 1 for all x. So that's why we are using 1 as our nth derivative evaluated at 0. Okay, so let's keep going. What will we have next? X squared over 2 factorial plus x cubed over 3 factorial plus ... And what do you notice? This is x to the n over n factorial. So e to the x is equal to the sum, n equals 0 to infinity, of x to the n over n factorial. You can kind of see how we arrived at that. Going to bring that down here. Okay. Okay, how about, and let's also mention here that the interval of convergence is going to be negative infinity to infinity. And we will talk more about that, but you could see that this limit is going to be equal to 0 when we take a look at the ratio test, and we can work that out. But for now, I would like you to just know that that is true. So let's go ahead and fill in our table for e to the x. The series expanded, and then the notation. So we have n equals 0 to infinity of x to the n over n factorial, and our interval of convergence is negative infinity to infinity. And we'll go ahead and write a few terms. Okay. Now let's go back up to the sine of x. So we have to come up with several of our derivatives to kind of see if we can see a pattern. So if f of x is equal to the sine of x, first derivative, cosine of x, second derivative, negative sine of x, third derivative, negative cosine x, and so forth. Okay, so f of 0 is 0. The first derivative of 0 is 1. Second derivative is 0, evaluated at 0. And that third derivative is a negative 1. So coming up with these terms, we can now say that the sine of x is equal to 0 plus, and now we have the first derivative evaluated at 0, which is 1. And we have times x. Of course, that's divided by 1 factorial, so I'll just put an x. And then, of course, we have a 0, and then we have a minus 1 times x cubed over 3 factorial plus 0 plus 1x to the 5th over 5 factorial, and so forth. So what do we have for the sine of x? We have that the sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so forth. If I can move that up just a little bit. Well, I think I will just leave well enough alone. Okay, so now let's look at sigma notation. So the sine of x is going to be equal to the sum n equals 0 to infinity. And let's take a look. We have an alternating term, So we need the negative 1 to the n power, and you do need to check that. When n is 0, that alternator is 1. So that's why our first term is positive. Divided by 2n plus 1 factorial, and we have x to the 2n plus 1. I got a little crowded in there. So let's go ahead and fill in our table for that one. So for the sine of x, we have, let's just fill that in, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so forth. Okay, that series in sigma notation can be written sum from n equals 0 to infinity. We have negative 1 to the n, and then here we have that exponent that gives us odd powers. And also, this interval of convergence is also negative infinity to infinity. Just make sure you know that. And we will talk more about that. Okay, so now you can convince yourself that you will be able to come up with these series and memorize them. Let's go ahead and get this written down. Before we derive this and go through all the derivatives, I want to show you something. For a Maclaurin series, we have x equal to 0. And we always said that this first term was f of 0. So that's the sine of 0, which is 0. So this 0 term is a 0. You could also think of this as remembering this as, and how I like to do it, is the sine of 0 is equal to 0. So x and x are both 0. Sometimes that helps. Also, the sine is an odd function. And all exponents are odd. And that's the same for the cosine, of course. Okay, so with that little bit of help I just gave you, what do you think about the cosine of x? The cosine of 0 is 1, so that first term is going to be 1. And of course, we are also alternating. We are an even function, so maybe that's helping you. Whoops, I forgot 6. Okay, let's go to sigma notation. N equals 0 to infinity. And we have negative 1. And I think I might have forgotten that negative 1 to the n on the sine of x. So this is negative 1 to the n. We have x to the 2n, which gives us those even exponents divided by 2n factorial. Our interval of convergence is also infinity. Okay, let's get this next one written down, and also let's make a note here about the sine of x. I think that's probably okay here, but let's make a note about the cosine of x. Y equal to the cosine of x is an even function. So you note that the exponents are even. So that's a nice way to identify it. You'll really like this next series, and 1 over 1 plus x can be written as 1 minus x plus x squared minus x cubed plus x to the fourth. Actually, I'll just put and so forth since we're on that positive term. So this is n equals 0 to infinity in sigma notation, -1 alternating to the n, x to the n. Now this radius of convergence is from -1 to 1. So that's important. So you will have to memorize all of these, okay? This shouldn't be too difficult. You could kind of take a look at each one and come up with some sort of way to memorize those. Now we have a little something that we want to talk about that's kind of neat, and it's this function 1 over 1 minus x. It is actually a geometric series. And so let's take a look at this. If you can remember, we had the sum of a times r to the n power, and we were able to say that that was equal to a r, and whatever that power was, that's k, over 1 minus r. Of course, if it was convergent, if the absolute value of r was less than 1. Okay, then it does converge. So sometimes it's nice to be able to talk about the series n equals 0 to infinity of a r to the n, and that's just equal to a over 1 minus r, since a is 1 and r is x. Okay? So what could we write? We could write that 1 over 1 minus x is equal to the sum of x to the n equals 0 to infinity, and that's just 1 plus x squared plus x cubed, and so forth. So, and this a and this r is for f of x equals 1 over 1 minus x. So this would be 1, and that's our x. Okay, so now we're going to really get to where we're going with this, and why would we need to have these memorized and mess with these a bit. So let's take a look real quick and try to come up with the sign of x squared. So what do we know? Since the sign of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7th factorial, and so forth, since that is true, then the sign of x squared, we're going to replace all of our x variables with an x squared. So we're going to have x squared minus x squared cubed over 3 factorial plus x squared to the 5th over 5 factorial minus x squared to the 7th over 7 factorial, and so forth. So we have x squared minus x to the 6th over 6 factorial plus x to the 10th over 5 factorial. Whoops, that should have been a 3. Minus x to the 14th over 7 factorial, and so forth. So, how could we write also the sign of x squared is going to be, and let's go ahead and see if also since the sign of x is equal to n equal to 0 to infinity, let's bring that down just a little bit, and that's equal to -1 to the n, x to the 2n plus 1. I'm really running out of room now. Let me move that and erase this. There we go. Then the sign of x squared is going to be -1 to the n, x squared to the 2n plus 1. Whoops. And that was 2n plus 1 factorial. Okay. All divided by 2n plus 1 factorial. Now we don't mess with the n's. We are only replacing our x with x squared. That's it. And so what would we come up with? -1 to the n, x. Now remember, we multiply exponents. So this would be 4n plus 2 power divided by 2n plus 1 factorial. So really, really makes it kind of cool to be able to use these functions that we already know. Okay, look at this one. X squared times e to the x. Well, since e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... x squared e to the x is equal to x squared plus multiply x squared times x cubed plus x to the 4th over 2 factorial plus x to the 6th over 3 factorial. Whoops. Be x squared plus x cubed plus x to the 4th over 2 factorial plus x to the 5th. I'm just jumping to the next. Plus ... Also, since e to the x is equal to, and what did we have for e to the x? We have x to the n over n factorial. Then x squared e to the x is going to be x squared times x to the n over n factorial. And we will just add those exponents. So that's x to the 2 plus n, or let's write n plus 2. It'd be nicer. All over n factorial. So that concludes this topic.